Thank you for the introduction. I'll be talking today about the SAFT coarse graining technique and how to use it to understand simulations of fluids. I will start talking a little bit about the context in which this presentation is placed. In general, different people have different understandings of what simulations is. Simulations, the molecular simulation, will depend on the point of view of the observer. And in principle, it will be very significant in terms of the time scales and length scales that we're observing, in such a way that there is a nice correlation between the length and time scales, which can be approximated or thought about as being a ladder which leads from the very small time and length scales associated with the vibrations of molecules, all the way up to the macroscopic behavior of plants and large systems. This ladder, this relationship between the different scales, is not a continuous one. We have at the bottom of the scale both ab initio and DFT calculations, which are very accurate and are able to describe the small details of individual molecules. But when we want to pass from DFT or similar types of calculations all the way to a description, atomistic description of matter, we find that the rung in that ladder is broken. And it's very difficult to obtain a very smooth way of passing information from one to the other. From the atomistic modeling, in which we describe individual molecules and as groups of atoms, to a coarse-grained description, which is what this presentation is going to talk about, there's still links and there's still possibility of passing information. But from there on, it is very difficult to pass information from this molecular type of understanding of matter all the way to the higher scales. So unfortunately, this is a matter for another presentation, and we'll talk today about coarse graining force fields. So what is coarse graining about? The bottom example shows an idea of what we can achieve with coarse graining. By coarse graining, we remove the detail in the molecular model and try to focus on what is important on the traits of both molecular conformations and energy, which are important to look at the macroscopic observable properties. So in this case, we have a liquid crystal, which is formed by a rather rigid ring, a large ring with a long alkane tails put around it. So instead of modeling atomistically, which would require enormous computational effort, we build a coarse-grained model which has the general traits of that particular molecule. And this larger coarse-grained model is much easier to simulate. And there's less force centers, and there's orders and orders of magnitude of difference in the computational effort needed to model it. And by allowing for that, we can actually understand, for example, in this case, the formation of very unique liquid crystalline phases, which are formed by the interpenetration of these large holes in these unique molecules. So coarse graining is essential if we're looking at large molecules or we're looking at large timescales needed. For example, in the cases of polymers and multi-component mixtures, self-assembly of soft matter, it's indispensable. But there is a risk of garbage in, garbage out, because there is no universally accepted procedure or methodology to obtain the information for the coarse-grained force fields, and this is important. You see, because integrating out the degrees of freedom inevitably results in a loss of information, and this has its consequences in terms of the transferability of the models. There is generally two approaches in which you can pass the information from, or you can add the information to the coarse-grained model. The most naive, or maybe the more classical way of doing it, is probably described by the cartoon on the right-hand side, where you see an atomistic model of a peptide and the corresponding coarse-grained representation, where groups of atoms or important parts of the molecule are grouped into other force centers. There are several ways to do this upscaling. And the most classical way to do that is called iterative Boltzmann. And in the iterative Boltzmann technique, one attempts to match either radial distribution function or some other detailed atomistic representation of the model, and fits or by iteration fits a potential, a coarse grain potential, which matches that, with the hope that if we match the radial distribution function or some other property, we will get a good representation, a good overall fit of the force field. Force matching is similar. In this case, we actually try to match the forces among groups of molecules. Rather recently, the concept of relative entropy scaling has been championed by Professor Schell and employs a measure of entropy to obtain matches between the scales. And even more recently, machine learning has been brought into the equation, saying, well, maybe a machine is probably more clever than us and allows us to understand the relationships between these atomistic level details and the coarse graining models. Another way of thinking about the problem is a top-down approach. In this case, we look at the macroscopic observable properties and try to figure out what is the intermolecular potential that produces these macroscopic properties. Martini is the force field that exemplifies this idea. It guides the parameter estimation by matching experimental water octanol partition coefficients and other similar properties. The Martini force field is rather simple. There's a fixed set of equal-sized beads. The different energies and charges are assigned to these different types of beads, which themselves can be used to build molecules of different types. Our model is called SAFT, which stands for the Statistical Associating Fluid Theory, is a different approach. It basically maps energy, size, and range of beads to expected macroscopic volumetric properties, and we'll discuss this as a focus of this presentation. I might mention that DPD, or distributive particle dynamics, is also an interesting approach, but does require a ad hoc fitting of the parameters to macroscopic properties. So the SAFT approach deals with the classical idea of how to build an equation of state. Usually, if we start with experiments, you would be interested in using a theory. Now, this theory, if the theory tries to mimic the experiments, but most likely usually fails. And when that happens, one is not very sure, why is it that it fails? Is it because the theory itself is badly constructed? Or is it because the underlying potentials or that the theory is based on are not appropriate to describe the experiments? For example, if we were looking at a theory for hard sphere fluids and we try to use it to compare to experiments, in this particular case, no matter how good the theory is, it will never fit the experiments because real life fluids are hardly ever hard spheres. Here's where molecular simulations come in handy. Simulations can be used to generate pseudo data that can be used to fine-tune the theory. In this case, there's no ambiguity with respect to the difference between the potential in the data and the one that the theory is trying to fit. So we can fine-tune our theory using simulations. And once we do that, and we compare to experiments, then we can be very sure that the only difference between experiments and the simulations is the lack of our force fields to represent the reality of experiments. So once the cycle is complete, you can think about flipping the cycle around and saying, well, if we have a theory that represents well our simulations, and we can use a theory to fit well the experiments, then immediately we have found a force field that represents the experimental data. And this is what the SAFT coarse grain model is about. Basically, we can use this cycle to produce force fields that are in agreement with experiments. And the interesting thing is that once we have these force fields, we can invoke both the transferability and the representability of these force fields. So we can use the parameters that are fit to one molecule to another set of molecules, or we can also use these simulations to explore properties which are not included in the original fit. For example, interfacial properties, transport properties, etc. The basis of the SAFT model is, of course, the SAFT gamma me equation of state. This is a highly accurate equation of state. It's a third generation of the SAFT models. It's based on the me potential, which is up on the left-hand side, top left-hand side. The me potential depends on a distance of approach between two molecules, a value of the well depth or energy, or epsilon, but also depends on a range, which here is symbolized by the letter gamma. Different ranges change the form of the potential and allow the fine-tuning to different types of molecules. Now, the SAFT formulation is unique in the sense that it relates the macroscopic equation of state with an underlying force field. The parameters for the equation of state are given in the top right-hand cartoon, which again are the sigma, the epsilon, lambda, and the number of beads forming a chain. In the lower right-hand side is actually the crux of the matter. If we take experimental data marked by the solid black points, and we fit the equation of state, which is a solid line, we can produce parameters which reproduce this experimental data. These parameters are the same parameters for a force field. So we can use molecular simulations using those parameters to reproduce the red dots, which correspond to the equation of state, but also, of course, now correspond to the experimental data. So the first question is, how do we obtain the parameters for the equation of state? And we've already given you a clue about this. An idea would be to fit the equation of state to experimental data. We usually, we use in general, and we've seen that it's reasonably successful to use vapor, liquid, phase equilibrium densities, and vapor pressures, although we could incorporate in principle any property that comes out of the equation of state, like excess volumes, enthalpies, et cetera, or second derivative properties. And another way to do that, and we'll discuss that later, is to formulate this in terms of corresponding states, in which case we would need even less data. If we use experimental data, here's an example of the type of fits that we can obtain. These are three components which are not trivial to model. In triangles, you see the attempt to model this using the Leonard-Jones model. And you can see that no matter what we do, no matter what parameters we use, the experimental data, which are the dashed lines. If we use the SAFT equation of state, we can see that we can fit the experimental data, and the simulation data fit spot on the experimental data and the equation of state. The me potential, which is the basis of the SAFT model, is actually a conformal potential, meaning that different sets of exponents, m and n, in the equation produce exactly the same result. So the potential itself, what this basically means operationally, means that we can fix one of the exponents in the me potential. Usually we fix the attractive exponent, n, here in this slide, to 6, which tends to be a reasonable suggestion in terms of the London exponents, and leave as only as an adjustable parameter the repulsive part of the potential, in this case m, which we have symboled as lambda. This basically says that there is a unique parameter in terms of, there is one unique parameter, which is the energy, another unique parameter, which is the size or sigma, but there's a third unique parameter, which corresponds to the range of the potential, which either lambda or alpha, and you will use these in the same way. So this suggests that the equation of state can be expressed in terms of a 4-parameter corresponding states or 3-parameter corresponding states correlation. M signifies how many beads we have in a molecule and gives us an idea of the aspect ratio of the molecule. Sigma is a size parameter, epsilon is an energy parameter, and lambda is a non-dimensional, lambda or alpha are non-dimensional potentials which talk about the range of the potential. So it's natural to try to match these two critical properties. Value of M would be basically given by the molecular geometry of the molecule. Lambda, we have successfully fitted it to the eccentric factor, which is some sort of measure of the difference between the potentials of the different molecules. Epsilon is very nicely correlated with the critical temperature, and sigma, of course, is very nicely corresponded and related to the density of the molecule. And if we can do that, then with a very small number of properties, the eccentric factor, critical temperatures, and one single density point, we can obtain all the parameters for the molecules. And we have done that for a large number of molecules and collected this in a web page called a bottled SAFT. There's a joke associated here with because SAFT, of course, means in Nordic languages means juice, where this is the name comes from. So in this web page, you can enter as input critical properties. Otherwise, you can enter by just simply names, and there's a database of properties. But if you wish to input yourself the data, we would need three pieces of information. One is a critical property, the critical temperature. The other one, an eccentric factor, which is basically a point in the vapor pressure curve. A density at 0.7, the critical temperature, which the liquid density, which again is just 1 point in the density curve. And with this information, we can obtain the 4 SAFT parameters that we would need for the model. The quality of fit is seen here for the case of R134A, which is a common refrigerant. The molecule is modeled as 2 tangent homonuclear beads, M equals 2. And you can see in the graphs the predictions now from the equation of state as compared to the experimental data in open symbols and the simulation data, which is the solid symbols. And this, as I mentioned, is tabulated, and we have over 5,000 well-defined components for which we have parameters. And of course, we could just add more if we knew some sort of information on the thermophysical properties to either fit the data directly to the data or to use a corresponding states approach. And the quality of the fit is actually very good. This is a very dense plot of the normal boiling point as compared to the experimental one with an extremely good quality of fit. There's over 5,000 points in this graph, although it's not apparent from the fact that all the numbers fall almost one on top of the other. We're not completely linked to the SAFT equation of state. You could use extensions of the SAFT equation of state to use exactly the same concept. In this plot, we are looking at cryogenic fluids which are at such a low temperature that quantum effects start becoming important. So we've taken the equation of state and added the Feynman-Gibbs correction to take into account these quantum corrections. The Feynman-Gibbs correction also influences basically directly the intermolecular potential and produces, in essence, a temperature-dependent potential. By doing that, we can actually model mixtures of cryogenic fluids at extremely low temperatures with an accuracy which rivals both the experiments. And the nice thing that we can do it with not only, of course, with the equation of state, but the important thing here that we can do it with the simulations with a force field that defines these mixtures. So how about other things like, for example, transport properties, interfacial properties? It's important to recognize that transport and interfacial properties were not part of the fit. The fit is based on the equation of state, so we basically only use volumetric properties for the parameterization. But the procedure is apparently very broad, and it's what we were basically doing is fitting the effective Helmholtz free energy landscape. So this seems to be an excellent idea to produce a robust optimized force fields, which can then be later used to explore other properties. As an example, I'll show you the observation that we had in terms of understanding high pressure CO2 water interfacial tensions. The plot on the left shows in black and white experimental data of interfacial tension as a function of pressure. And what can be obviously seen from the graph is that there's an enormous amount of dispersion, especially around the 10 megapascal range. And this is quite puzzling because all of these groups are very good groups with extremely accurate equipment. So this inaccuracy is completely atypical in this situation. The coarse graining model allows us to study large systems. And in this case, we studied a relatively large system at the conditions close to these experimental data points, finding the interfacial tension and density profiles for all these systems. And what we saw was that in the vicinity of around 6 and 7 megapascals, the system passed from being a vapor-liquid system to a liquid-liquid system through a point that corresponds to the vapor-liquid-liquid equilibrium. And of course, at that point, seen a snapshot, which is seen at the top right-hand of the slide, we see that we have actually, of course, 3 phases with the corresponding new number of interfacial tensions, each for each pair of phases that can be considered. So of course, what was happening in the system was that we're not looking at a simple 2-phase system, but we're looking at a 3-phase system. Hence, the characterization with a single interfacial tension was of course impossible. And that of course explained why there was this very big spread in the simulation in the experimental data, most likely because of the appearance of another phase in the system. Another example of how the accuracy of these transport and interfacial properties is the results of the 9th AICHE Industrial Fluid Property Challenge. In the left-hand side, we have the predictions that come out of the SAFT models in terms of the interfacial tensions as a function of temperature for water, toluene, and dodecane. The challenge itself was to try to predict the interfacial tension of a mixture of these compounds at high temperatures and high pressures, for which the answer was unknown. Once the predictions were made, the experimental answers were disclosed, and a comparison could be made of the different modeling techniques. I was very pleased to see that the SAFT model came top in this challenge, rivaling the very accurate atomistic and other types of models. Transport properties are also reasonably well described. In this example, I'm showing the self-diffusion coefficients of rather long alkanes, sometimes called waxes. In this case, it's the self-diffusion coefficient of C24, very close to its freezing point. To the left hand of the graph, we have the low temperatures corresponding to the solid phase, and to the right hand, we have the fluid. It is compared against, in the orange dots, which corresponds to DOSI NMR results, which are actually experimental data. The symbols in green correspond to the different simulation results, ones with atomistic, fully atomistic models, and in green we have the SAFT models. And you can see a very nice agreement between the DOSI NMR simulations and our results. This was taken, you can take it even further to look at mixtures of these models. So this is the example, the output of a simulation of an 8-component alkane mixture fitted to a real Malaysian crude. And the interest here was to look at the wax appearance temperature, which is basically related to that point in the self-diffusion curve where there is a change in the slope. So we saw this change in slope, the experimental mixture in red, matching very nicely to the NMR data for the fluid region and predicting a wax appearance temperature quite close to the experimental data. I just might mention that in these simulations of diffusion, if one is actually on the same plot, one is quite pleased. You can actually see that the diffusion coefficient scales several orders of magnitude, so it's actually very hard. It's a very stringent test of the theory. So I've given away a little bit about how to consider complex molecules. An idea to fix complex molecules is that unfortunately we fit parameters on a per molecule basis with homogeneous models. But there's no reason why one could not invoke a group contribution approach. And in this case, I'm going to show you, for example, the case of an example for a toxylated surfactants. A surfactant, as you of course know, is a molecule which is polyphilic in nature. In this case, the etoxy is a non-ionic surfactant formed on one side with ether groups, and on the other, which are hydrophilic, and on the other side with an alkane tail, which is hydrophobic. So we decided to take this molecule and split it up into pieces. The alkane part, we fitted these beads to the properties of different alkanes of different lengths. The central ether molecules, we fitted it to the different available ethers in the experimental data available. And the end group, which is basically a glycol group, we fitted it to the properties of triethylene glycol. And what we did was assume, and here's a leap of faith, that by joining these groups, the resulting molecule would have the correct behavior. When we build these heterogeneous molecule models, immediately we have to start thinking about the properties, the cross properties, the properties between these two groups. And again, that can be fitted to the experimental data from smaller molecules. So at the right-hand side, you see the fit that we used to fine-tune the triethylene glycol mixture by using the excess enthalpy as a function of the mole fraction. And these parameters, these thermogenic parameters, were then transferred into the general model. It's very interesting to see that using these parameters and without further adjustment, we were able to look at the different morphologies of these surfactants in water. We went all the way from the micellar region to the worm-like regions to being able to predict lamellar phases and inverse micelles, all with the same set of parameters. In the following slide, I'll show you a movie of what happened in our model when we put it into the water-air interface and put an excess number of surfactants at the interface. What happens, of course, is that we exceed the CMC, or critical micelle concentration, and the micelles will start detaching from the surface in order to maintain a maximum amount at the interface. This movie we were able to produce this movie because our models allow us to expand our timescales enormously. A movie like this would be more than a heroic attempt if we wanted to do it with an all-atom simulation. It would be very difficult, both in terms of the size of the systems that we would be interested in, and it'd be enormously difficult in terms of the timescales. We're talking here about effective timescales in the order of microseconds, which can be explored with relatively ease and with the type of computing power that we can nowadays access. Polymers are a classical extension of these ideas. Polymers are by their own nature formed by smaller groups, in which each of these smaller groups can be fine-tuned to the properties of either a monomer or the constituent molecules. Polystyrene here is atactic polystyrene is a very nice example. Here we used an alkane backbone, which we fit to the alkane molecules themselves, and we decorate this alkane backbone chain with small toluene molecules. But our model of a toluene molecule is based on two tangent spheres. So instead of using two tangent spheres, we basically, by trial and error, we figured out that using half a toluene molecule spread on each one of these beads would produce, on average, a model that was satisfactory. We placed this polystyrene model in both hexane and heptane as solvents, again, using a coarse grain model for this. Without any general fitting, we looked at small molecular weight polystyrenes in hexane. In this particular case, this mixture produces both an upper and a lower critical solution temperature, meaning that at high temperatures and or low temperatures, we see a phase split, while in the intermediate temperatures, we have a homogeneous mixture. We performed very large simulations for these systems, and it was also a challenge to try to understand what is a phase-separated system and what is not. And a nice way of studying this is by looking at local density histograms and plotting these local density histograms. So in the figure in the middle, in the blue figure in the middle, the question is if this is a one-phase or a two-phase system. By looking at the density histograms, you can see that there is a mean histogram size, and there's some spread around this mean, but in general, there's only one histogram distribution. However, for the top and the bottom, it's evident that the system looks like it's in a two-phase system, and by looking at the histograms, we of course see that there's two peaks, one peak corresponding to the pure solvent and another peak that corresponds to the polymer phase. Interesting result is that if we change now the solvent for heptane from hexane to heptane, instead of finding this upper and lower solution temperature type diagram, we find what is called an hourglass diagram, and in which we have a regions for volumetric fraction regions for which there is always a phase separation, but some others where there is a change between this two-phase system and this and a one-phase system. Again, I might stress that these are reasonably large simulations with reasonably large time steps, which would be very challenging to, if not impossible to do nowadays with fully atomistic models, but are reasonably easy to do with coarse grain models, and most importantly, are very accurate and predictive. Another area which we've been exploring the use of these models is for simulations of oil fluids and crudes. This is an example of our representation of a live crude. We have broken down a continuous mixture into 12 discrete components, which span from smaller light ends corresponding to gases, medium and heavy ends corresponding to other alkanes and aromatics. And more importantly, we've also included the very heavy ends, which corresponds to the resins and to the asphaltenes. Both resins and asphaltenes are polynuclear aromatic-based molecules, which, at least the latter of the asphaltenes, have the tendency to precipitate out of solution if the conditions of pressure and temperature are the appropriate ones. And this precipitation is usually a concern for production of oils and is something that is in general um, of interest to avoid. One of the things that we wanted to study was the effect that morphology of the different asphaltenes had on their propensity to precipitate. You can see that there's two asphaltenes in this slide, which I'll zoom in on the next one. These two asphaltenes are basically almost isomers one of each other. One of them is what the top one is what's called an archipelago model, and the bottom one is called a continental one. And the difference relies on the way that the aromatic rings, or the polynuclear aromatic rings, are ordered. You can see that from this molecule how we've built an asphaltene molecule out of pieces. They're both Frankenstein molecules built from smaller pieces, which we recognize when we look at the fully atomistic description of these molecules. It would be extremely difficult to isolate these molecules and to try to fit them, to find properties of them, volumetric properties, which we could fit with the equation of state. So in this case, it's very obvious that this group contribution approach to these larger molecules makes a lot of sense and allows us to build molecules from smaller building blocks. We performed extremely large-scale simulations in these systems, and for some conditions, we actually saw the expected aggregation. What we saw was that for the continental, were the ones we called bad asphaltenes, the red ones in this plot. We could see that there was a significant aggregation, self-aggregation of these systems. Well, for the other molecules, the archipelagos, which are the same molecular weight, different conformations, would remain in suspension and would not really form part of these large clusters. Resins, which are intermediately small molecules, and in some probably wrong theories, are described as peptizing or agents that could solubilize, or these clusters are seen to be very well spread and very well diluted in the system. Toluene is seen to form part of these clusters, while alkanes, for example, are seen to stay away from the clusters. To perform this simulation with an all-atom model would have required in the order of several millions of particles, something which is well beyond what we would normally want to do for the time scales that were needed for the to see the aggregation. I'd like to discuss also some issues that we know are happening with our model, because our model, of course, is not perfect by any means. There's two things that at this point that I'd like to just point out as significant problems that we've come up with. One of them is the premature solidification, which is enhanced by the fact that our models are, especially our homogeneous models, are made up of spheres of the same size. And this spherical nature of these segments, when we are looking at very high pressures, have a propensity to form a solid. And we have seen that this premature solidification affects, especially when we're talking about extremely high pressures in the order of gigapascals or things like that. And there's nothing we can do at the moment for this. It's just a fact that there is a little bit of too much symmetry in our models for this. The other thing that is somehow missing is the explicit introduction of charges or electrostatics. In principle, there's nothing impossible about this. The issue is that it's very challenging to develop equations of state for these systems. Hence, it's very difficult to have the equation to be able to use it in the simulations. We have stepped across this model, for example, by looking at water. In this case, we employ average potentials, which implicitly include the charges. But we definitely recognize that this is a region which probably requires some sort of improvement. There's other things which are on our to-do list to improve on the model, and some researchers have been working on this. One is to look at fused or maybe less coarse-grained models to exploit the fact that the equation of state can describe molecules as fused molecules, and to use that information to build more detailed models that could incorporate a little bit more of chemical specificity. And the other one, which it's somehow shameful, is that the equation of state is actually an equation of state for associating fluids. It's called the statistical associating fluid theory. And the information about how to include association terms is built into the equation. So nothing stops us from thinking about coarse-grained models with sticky sites, which can mimic association models. And that can definitely be done, and it's actually work in progress. And another idea, of course, is to forget about the equation of state altogether, to bypass the equation of state, and to use machine learning techniques to jump directly from simulations to the correlations or experimental data and back. That is using machine learning techniques to take a top-down approach to use experimental data and predict intermolecular potentials. So as a conclusion, I just wanted to mention that the use of top-down approaches relieves some of the fundamental issues associated with coarse graining. And particularly the washing out of information when going from a finer to a more coarse-grained model disappears. In fact, the SAFT coarse-grained approach basically uses the integrated information contained in macroscopic thermophysical properties and obtains a surrogate or an effective potential that predicts these macroscopic properties. And by doing that, it ends up with a potential which is both covers the three holy grails of a molecular model. That is that it is transferable, that is representative, and that it's accurate. The use of an analytical equation of states to make a link between these macroscopic properties and the intermolecular potential is key to the success. But also it's the limitation, because our model will only be as good as the equation of state that it's based on. An example of this is, for example, that charge systems, as I mentioned, are particularly challenging. If you go into our webpage, into the molecular systems engineering.org webpage, you'll see a list of the current applications of the SAFT force field and the systems that we've been using. I'd like to finish my presentation concluding, of course, that this work is not a one-man show. It's the effort of an enormous amount of people, a very large group, and most of the people that have done the hard work are shown in this slide. So thank you very much for listening.